Following on from the previous video, our aim here is to try and differentiate this natural log of x here. So at the moment, our aim here is to try and differentiate this graph here. So at the moment, what you've got is you've got a graph of y equals the natural log of x. Okay, so our aim here is to try and differentiate this. Okay, so let's start out with this. Hang on. So here we are trying to differentiate y equals the natural log of x. So in the past, whenever someone gives you this statement here, we can always translate this. So to translate this, in the past we would zoom in. Your eyes would zoom into this base here. Now, when there's no base, you have to default it to a 10. So to translate this here, your eyes should zoom into the base here. In this case, we're going to default it to a 10. So what it means is 10 to the power of what will give us this thing here. Will give us this thing here. And whenever you talk about log or the natural log, you're always interested in the index. So in this case, in this case it is 2 here. So this is 2 here. Well, hang on. Whenever given this statement here, to translate this, your eyes should zoom into this thing here. So we would have to default it to a 10. So to translate this here, we would have to think inside your mind. You would have to think 10 to the power of what will give us this thing here. Will give us that thing here. Well, whenever you talk about log or the natural log, you're really talking about the index. So in this case, the index here is 2. Okay, so given this here, we can translate it to this. Well, this thing here is this 2 here is a bit like the y here, and this is a log here, but it's a special case where the base is e. Okay, so here in this case, the log here is base 10. This is a special. You can imagine this as being base e, if you like. And then this 100 here is like this x here. So whenever we get given this here, let's translate it. Your eyes should zoom into the base. In this case, is base e here. So to translate this here, it is e to the power of what will give us this thing here. That's us translating it. Okay, and then in this case, it's y. The index here in this case is y. Okay, so to translate this here, we would have to zoom into the base, which is here. So it's saying e to the power of what will give us this thing here. Will give us this thing here. In this case, it's y. So when given this here, you can translate this as e to the power of y equals x. So this is in a way the same as this here. So we just translated it. Okay, so to differentiate this here, we would translate it to this. Now, once in this form here, we can use implicit differentiation to work out the derivative of this thing here. So remember that this e here is to the power of y here, meaning, well, y here is a function of x. So when you've got to use a chain rule here because of the y here. So using the chain rule here, so at the moment you've got e to the power of y equals x here. Now implicitly differentiate this, bearing in mind that this is a function of x here. So you've got to use the chain rule. So let's differentiate this. When you differentiate this, it is just itself. So when you differentiate this here, it would just be itself. But then you've got to times by this bubble here, if you like. That will then give you, well, whenever you differentiate e to the power of y equals x here. If you differentiate this here, it would, well, the beauty of e to the x is that when you differentiate it, it would just be itself. It would just be itself. So when you differentiate this here, it would just be itself, and then you've got to times by dy by dx. It would then give you this. Now differentiate the x, it will give you this 1. Okay, hang on, let's start again. So our aim here is to differentiate this. Translate this, it will give us e to the power of y equals x. Now differentiate this. Well, remember, if you differentiate this, it will be itself. So, and then you've got to times by dw by dx here, because in this case w is a function of x. Well, y here is a function of x. So when you differentiate this here, it will be itself. Differentiate this here, it will be itself, but then you got to times dy by dx, because this bubble here is a function of x. So anyway, differentiating this here, differentiating this will be itself, and then you've got to times dy by dx. Differentiate this here, it will just be 1. Okay, so that will then take you to here, and then and now your aim is to get dy by dx on its own. So divide both sides by this thing here. So dy by dx is this thing here. Now from earlier, remember from this we translated this into e y equals equals x here. Remember, when given this here, you can always translate it to this. Now, e to the power of y is x. Look at this. Looking at this statement here, looking at e to the power of y equals x, e to the power of y equals x, hang on, e to the power of y equals x, e to the power of y equals x here. Look at this, e to the power of y. Well, let's put x into here. So e to the power of y is x. So put it into here. So basically dy by dx equals this. Dy by dx equals 1 over x. So looking at this graph here, when you differentiate this graph here, looking at that graph there, dy by dx, the derivative of this is 1 over x. Okay, so it's kind of strange. We started out with e to the power of x. We in a way manufactured this inverse function, but then the derivative of this inverse function is 1 over x. Okay, so bear this in mind. This is bear this in mind because we will need this in the future. So the derivative of the natural log of x is 1 over x. Okay.